So we've been ignoring the direction of the electric and magnetic field. Okay, we've just been talking about this is the ray representing the direction that the light is propagating. This is the wavefront, which represents parts of the electromagnetic wave, which are all in phase. However, it's important to remember that when we're looking at light propagating through space, okay, we're looking at, for instance, we talked about the Poynting vector represents the direction that the light is traveling. That while this is happening, we also have an electric field. Okay, I'm going to do my best to represent 3 dimensions on a 2-dimensional surface. So in this case, our light wave is propagating in the negative x direction. Here, the electric field is oscillating in the y direction. And then, of course, our magnetic field is coming out of the screen and oscillating in the z direction. So what that electric field is doing is very, very important to how the light is going to interact with the atoms or molecules in some medium they're propagating through. And in some cases, it's important because the medium it's propagating through might not be isotropic, meaning all the same in all the in all directions. Okay, it might have some preferred axis where the electrons are restricted, where they more easily oscillate in one direction than another direction, or they might have different resonant frequencies depending on which direction that they're pulled. So the polarization of light really talks about how this electric field or magnetic field is oscillating. Now, in most light, like in this room right here, there's no polarization. I've got some electric fields which are oscillating in one direction, some oscillating perpendicular to that. It's just completely randomized because the light in this room is unpolarized, okay? Some photons have one polarization, some photons have another polarization. If I were to measure the electric fields, they would all cancel out because of the different directions. But when I polarize light, what I'm doing is I'm saying, well, I'm only going to restrict the electric field to oscillate a certain way. If it's linearly polarized, and linear polarized, as we'll see, is only one, is just one way that we can polarize light. If it's linearly polarized, I'm going to say that my electric field can only oscillate in one direction. In this case, only oscillate up and down here, okay? I could also have linear polarized light in a direction perpendicular to this. I could polarize it this way, okay? As long as it's just restricted to oscillate like that, that is linear polarized. But again, I choose one direction, and that's the only way that my electric field can oscillate. And this is what we call linear polarization. Now, how do I polarize light? Well, it actually happens by some pretty common instances. Selective absorption is where I have a material, something that's called dichroic. It is going to absorb one of the polarizations, leaving the other polarization intact. So for instance, if I absorb all the polarizations in the x direction here and leave the y directions unchanged, I will get linearly polarized light in the x direction. I can do it by reflection. Interestingly, when light makes its way onto an interface, a surface, okay, the atoms, the electrons, they can't oscillate in and out of the surface. They have to oscillate perpendicular to the surface. So right at the correct angle, I can get 100% polarization if I'm at what's called Brewster's angle. So reflected light tends to be polarized. Why do we wear polarized sunglasses? Because reflected light usually produces glare, which is unwanted, makes it more difficult for us to see. When we put on the polarized sunglasses, we filter out that reflected light off of shiny surfaces. And finally, the light in the sky, the light scattered, the blue light scattered by air molecules is actually polarized too. Okay, so let's take a look at this. This is what is known as selective absorption. It's a dichroic filter, and it is going to allow this polarization through, but it's not going to allow this polarization through. So if I send the light through and it's in the up and down direction, the light's going to make it unimpeded. Okay, well, there's always going to be some absorption. I've got to be fair here. But this polarization is just going to be completely absorbed, and it's going to cease to propagate. So that is what we call a linear polarizer. And again, here's natural light, which has no polarization to it. After sending it through this polarizing filter, only one of the polarizations is going to remain. So how do we get something like this? Well, we have E.H. Land to thank for this. And probably before your time, I'm a little bit older than most of my students. And E.H. Land was really the founder of not only the polarizing filter, what we call the Polaroid, he also developed the Polaroid camera. And has nothing to do with polarization, but these instant cameras were really, really big, where you could develop your film instantly. In any case, he invented this in 1928, and he's actually holding one of these Polaroid materials. And the way it works is that if you think about this, most plastic films are long polymers. And if you stretch a polymer, what tends to happen is all the molecules, which, you know, if you look microscopically, would look like spaghetti, you stretch them out so they're all oriented in one direction. You then coat these polymers with something that is electrically conductive. Believe it or not, iodine was what he coated these with. Iodine, you know, is conductive enough to absorb one of the polarizations. So the light would come in, and everything aligned with the polymers would produce a small current in the iodine. This would be absorbed, okay? But everything that was perpendicular to the polymers would go through, and that would be the linearly polarized light. So here is a close-up of what some of these polymers might look like. First Polaroid sheet, which was called H-type. I don't know why they used H-type, but it was a sheet of polyvinyl alcohol that was laminated onto cellulose acetate, and this became the basis for the first Polaroid filter. I don't know what they make them out of today. There are other materials that are natural Polaroids, if you will, and these are called dichroic crystals. Tourmaline is dichroic in that it tends to absorb one of the polarizations while letting the other polarization through. Now, Malices Law tells you how much light is going to go through two polarizers. If I have two Polaroids, which both have the same axis aligned, the first polarizer is going to linearly polarize the light, okay? So that's what we're going to say. At this point right here, my intensity is I0. And then the second polarizer, if it's aligned, will not affect the light at all. However, if I rotate it on its axis, the second Polaroid is going to absorb some of the light that passes through, okay? And this will lead to less of intensity. So you can actually use two polarizers to make a variable filter, a filter that allows more light through or allows less light through simply by rotating the second Polaroid. If I cross both polarizers, and this is going to be very, very important for the liquid crystal display, no light is going to make it through the system. Okay, so that is the intensity as a function of the initial intensity. And that's the initial intensity that makes it through the first polarizer, to be fair, times cosine squared of theta, the angle between the two polarizers. Now, polarization by reflection, as we said before, if I have some reflective surface, some interface, we have to think about the way that the light is going to hit that interface. It's going to hit it, okay? It's going to hit it like this and then reflect off of it like this. Well, the problem here is that if I draw my little atom right here, a molecule, it's going to act like an oscillator, okay? It can only oscillate perpendicular to the surface. It can't oscillate up and down, which means that my reflected polarization is going to be parallel, basically, the interface that's here for a certain angle. We call that Brewster's angle. Now, how much the light is polarized is really dependent on how close to Brewster's angle you are. All reflected light has some polarization to it, but Brewster's angle, known as a polarization angle, is equal to the inverse tangent of the index of refraction of the second material. Okay, we don't usually include the index of refraction of the other material because normally it's air, it's near 1. But if we were to include that, it'd be N2 over N1. N2 is the substance at which we're reflecting off of. Okay, and again, it's known as the Brewster's angle or the polarization angle. And again, we can see unpolarized light hits a reflective surface. Away from Brewster's angle, it's going to be partially polarized. Okay, you'll have a little bit of the normal polarization as opposed to the parallel polarization. But Brewster's angle, you get 100% polarization. The interesting thing is, even the refracted light is going to be somewhat polarized because if you're taking out some of the polarization in the reflected light, you're going to have a difference in, it's going to have the opposite polarization in the refracted light. And you can see this. This is a picture showing the reflection off of a pond or a lake or whatever. But here we look at the reflected glare without a polarizing filter. And here they placed a polarizing filter in front of the camera. And you can see into the lake much better with the second one because you're filtering out that polarization, which tends to be glare. And again, just makes it easier to see. Polarized sunglasses are more expensive than regular sunglasses, but they reduce a lot of the glare. And they also reduce some of the polarization from the molecules in the sky. Okay? Again, they tend to allow the vertical polarization through where the horizontal polarization tends to be that reflected or scattered. Again, a little hard to see here. I hope I haven't put myself above this. But as light comes in, light from the sun is unpolarized. It's the air molecules, and the air molecules above us, the ones that oscillate, okay, perpendicular to the direction that the light would travel down to us, okay, that is going to produce a polarization that reaches our eye. The other polarization is not going to be transmitted down to us. So the closer you are to 90 degrees of the scattered light, the more polarized it's going to be. So generally in the sky, the light near the sun, the scattered light near the sun is going to be relatively unpolarized. But at 90 degrees from the sun, you'll typically reach maximum polarization of the light. Again, you can see this in this case right here. As we said before, crystals can naturally polarize the light, but because the crystals have three-dimensional repeating patterns, the bonds in one direction might be stronger than the bonds in the other direction, giving them different resonant frequencies. So for instance, in this case, this crystal would have a higher frequency resonance in the Y direction than the Z direction, and the weakest would be in the X direction. So maybe the resonance for this crystal would be closer to the visible light in the X, and further from the visible light in the Y direction. This means that as light propagates through, different polarizations will see different indices of refraction. This leads to this neat effect that we see in calcite. In normal halite, there's no preferred direction. Halite's a simple cubic crystal, but calcite's more complicated in this crystal structure. So it actually breaks the polarization into two different linear polarizations, which will be refracted at different angles. So calcite, which is known as Icelandic spar for really good quality ones, is what we call birefringent. It refracts light along two different axes. And we can use these crystal polarizers to split beams of light into different polarizations. We can use them to analyze light. There are just a number of different ways that we can break the light into its different polarizations using birefringents or using Brewster's angles off of reflecting off of surfaces. So I said that linear polarization was one type of polarization. Typically, in an introductory course, we don't talk about circular polarized light, but it should be noted that a single photon of light is circularly polarized, meaning that the electric field actually rotates with respect to time, like we see in this diagram right here. Well, if photons are linearly polarized, how are we getting circular polarization from a photon? Well, if we have two photons, one that's rotating clockwise and one that's rotating counterclockwise, the superposition of the two will produce linear polarization. Okay? So you will see linear polarization is the easiest type of polarization to produce. It's the easiest type to explain, but we need to recognize that there is this form of circular polarization where the electric field rotates with respect to time. If that weren't complicated enough, we also have something called optical activity. And this is not polarization. It affects polarization. Let's say that we send in light at some polarization. In this case, it's in the vertical direction. If I send it through an optically active material, quartz is optically active, it will rotate this axis, okay? It's not absorbing the polarization selectively, it actually rotates the axis a little bit, and this changes the orientation of the polarization. If the optically active material is large enough, I can actually rotate it a full 90 degrees or even 180 degrees. Liquid crystals are a really good example of optically active material. And right now I'm in front of my iPad, I'm right in front of my laptop. Both use LCD display. LCD, liquid crystal display, okay? The beautiful thing about liquid crystals is we can use a small voltage, a small electric field to orient them in one particular direction or to change the orientation of the molecules. Here's how LCD displays work. Again, I'm oversimplifying the model, so anybody who understands these in greater detail, please don't get upset at my simplification here. So here's what we have. Usually we have some type of light source or reflected surface, okay? Here, let's just call this our light source rather than a reflected surface, because with reflected surfaces, typically we're relying on the room light to produce a display. I want an active light source from here. We polarize the light source, okay, using a Polaroid. And it enters the liquid crystal with this orientation right here, okay? Without any voltage, the liquid crystals are going to actively rotate the orientation of the polarization. Okay, they're optically active, so we get this rotation of the axis. So if we make the liquid crystal just the right thickness, we are going to get a rotation of 90 degrees, which means that none of this light over here is going to make it through the liquid crystal. What will I see? I'll see a black display. I'll see no light. Now, what happens when I turn this voltage on? Well, it now changes the liquid crystals, and they now become aligned with the field. So now the light coming from my source is going to make it through the first polarizer, okay, and then pass through the second polarizer too, okay? Makes it through both polarizers. And LCD displays now are color, and basically they allow, depending on what pixel we're looking at, a red, green, or blue pixel through. And this gives us the display that we want. Every time we turn on the voltage, that gets the liquid crystal aligned and allows us to see the light. Okay, so that is polarization. Lots to cover here. Typically in an optics course, we go into much more detail than we did here, but at least that gives you the basics. And again, I apologize. The circular polarization, I didn't cover in very much detail. Those of you with some optics knowledge know that there's even elliptically polarized light, but I don't want to go into more detail than we've gone here.